Thanks very much for coming, everybody, and thanks to the organisers for having me. It's a real honour to speak at Sigma Club. I've been to a lot of these now, and to be presenting one is really cool. Today I'm going to be talking about stuff which kind of straddles three different bits of my work, stuff which I did a couple of years ago, which is fairly concrete in my head, stuff which I've been doing over the past year, which is sort of in an advanced state of development now, but is not sort of finalised, and then stuff which the overall setting of it is currently in development. So hopefully there's lots to get into. I'm going to be talking about black hole evaporation and a proposal for a way of thinking about the justification of idealization, which I'm going to call the large-scale structure of deidealization. So you often hear that theoretical physics is in a crisis. Here's CERN at least talking about people talking about it, which justifies the fact that it's something you hear people say, whether you believe it or not. And the root of this problem is probably thought of as an empirical evidence problem for at least some parts of theoretical physics. So we have two, as I'm sure you all know, two broad fundamental physics frameworks right now, which are both empirically well confirmed. We have general relativity on one hand, which does cosmology, why apples fall, galaxies and black holes and all that good stuff, and quantum field theory, which is well represented by squiggly lines. On the other hand, which is the standard model, fundamental particles and forces, electricity, magnetism, what makes the stars burn, and all that good stuff. And so these two frameworks independently get a bunch of empirical confirmation, and they have done for the past 100 years. But for kind of reasons which I'm not going to go into in this talk, we think that our gravity theory, general relativity, should be quantized. We should have a quantum theory of gravity. And although there's some arguments say that there's some quantum gravity type experiments, the cow experiment might be one, the Page-Geiger experiment might be the other. Generally, we think that the empirical situation for quantum gravity is something of a barren wasteland. The energy scales are just not the sort that we can probe effectively in order to test quantum gravity effects. Now, despite this, quantum gravity and the domains and the combination of gravitational physics and quantum physics does have a bunch of energy of physicists going into it. And so it's worth thinking about what the status of all of that work is, given the fact that it's not being sort of championed by any experiments. And Hawking radiation and black hole evaporation is an instance of this. So in 1975, Hawking predicted, based upon particular derivation, that black holes will not, in fact, be black, but will radiate at some temperature called the Hawking temperature, and the radiation they give off is called Hawking radiation. Naively, you think that since the black hole is radiating energy, it should be losing mass energy, therefore it should get smaller and shrink. Now, these predictions have been basically taken up by the physics community and have been the basis for a bunch of fundamental physics research for the past 50 years. However, a solar mass black hole, which would be quite a small black hole by astrophysical standards, is going to be about 10 to the minus 9 degrees Kelvin, which is about 1 billion times colder than the cosmic microwave background radiation, which is the ambient radiation in the universe. So a black hole just sitting in the sort of the universe's room temperature, we would not be able to detect that radiation. Likewise, the lifetime of a black hole to totally evaporate is about 10 to the 60 years, which is about 50 orders of magnitude too high for us compared to the age of the universe. So we're never going to detect any of these two things directly. And so this is an instance of this empirical problem, right? There's a bunch of theory, and we're building on theory, and we're building on theory, but no experiments can confirm this stuff. Moving to a more general context, idealization seems to be particularly pernicious for understanding or confirming physics without experiments. So let's just think of like quite a naive model of how we might make a prediction of a model in physics. We might have a simple mathematical model say, a simple harmonic oscillator represented by this Lagrangian, and this is representing some real physical system, say a pendulum. Now, from this mathematical model, we might derive some consequence within the model, some consequence C. And this could be something like the period of the oscillation is independent of the amplitude. This consequence would then have some representational analog in the real physical system, so the independence of the actual amplitude of the oscillation of the pendulum from its actual period. And we would think, because we've derived this consequence from our model, that the representational analog should hold for the model. Now, this is obviously very simplistic and idealized as an account of how scientific inference works, but it's something akin to this. And this does seem to be how the derivations of Hawking radiation and black hole evaporation basically work. We have a model of a quantum field on a black hole spacetime. We derive either the existence of Hawking radiation or black hole evaporation, and we infer that the systems we take to be representing with our model, the astrophysical black holes, should in fact emit Hawking radiation and evaporate. However, all physics models are basically going to be idealized to some extent. So let's say that our model contains some feature f. In this case, it might be ignoring air resistance, which we take to be an idealization. It could be an omission of something which might be a difference maker, or it could be something which we just take to be false. And now, the consequences following from our idealized model. But we still have the same representational analog, the independence of the amplitude and the period of the oscillation. But now we want to know, is this going to hold for a real physical system? And because we've got an idealization in there, this isn't going to be that secure. And in practice, if air resistance is extremely strong for a real physical system, and if we care about a sufficiently high degree of precision of these claims, then it won't be the case that the period of the oscillation is independent of the amplitude of the oscillation. Friction is going to mess that up. And so idealizations can mess up this inference from being able to derive something from a model to believing that claim for the model. And so we need to figure out how can we have any confidence in our predictions derived from models when those models contain false claims or potentially omitted important details, idealizations, in other words. There's a naive way you might think about doing this, which might be called the empiricist approach, which is to just check. We can go to our pendulum in the world and just see whether, to the degree of precision we care about, amplitude is independent from period under the relevant conditions. And then we can be sure, okay, we were right, the idealization isn't messing up the inference despite this. But at the edge of empiricism, when we don't have any empirical evidence to support our modeling, then this option isn't going to be available. We can't just go and check that idealizations aren't messing up, for example, derivations of Hawking radiation. So we're going to have to take a different approach. Another obvious approach would be to retreat to deidealization. Now, deidealization, usually thought of, is going to be some procedure where you transform the model. You've got a model M, which is problematically idealized. So we're going to transform it by operation T to M prime. Now, M prime isn't going to contain feature F, so we're going to add back air resistance, right? And then we're going to check that C still follows from M prime. And then if it does, fine. We know that ignoring air resistance wasn't a problem. But there are at least two issues with this perspective on justifying idealizations. One is it's going to face a regress problem. Most, if not all, physical models are going to be idealized, and so M prime is still going to be idealized. So the exact same problem we saw before is going to occur here. But it also faces a descriptive problem. This doesn't look at all like the way scientists treat models. They don't infinitely worry about idealizations, then transform models and transform models. Obviously, deidealization in the form of transforming models does happen, but it doesn't seem to be a necessary condition for scientists having confidence in their models. So we both have a theoretical problem and a problem that we don't seem to be well capturing how science deals with idealizations. So we have a problem. How can we justify idealizations beyond our experimental capacities? Both of these approaches didn't seem to fare particularly well. A particular instance of this problem has arisen in the context of black hole evaporation. myself and the philosopher of physics Eugene Chua have both problematized the use of idealization in the context of black hole physics. In a forthcoming paper, I've argued that Hawking's derivation of Hawking radiation, along with other mainstream derivations, is inconsistent with black hole evaporation due to the use of idealization. And Eugene has argued that due to idealizations used in arguments for black hole evaporation, so my complaint was with the derivations of Hawking radiation. Eugene complains about the inferences from Hawking radiation to the fact of black hole evaporation. He thinks that these arguments don't support inferences to black hole evaporation in realistic, de-idealized black holes. And so we've got an instance of this general idealization concern, which might threaten skepticism about Hawking radiation and black hole evaporation. In this talk, I want to propose a sort of antidote to this sort of worry, a way of thinking about the justification of idealizations that hopefully is going to give us some hope that we're going to be able to do good theorizing unthreatened by idealizations, even without the support of direct experimental confirmation. I'm going to propose this way of thinking inspired by John Norton's large-scale structure of inductive inference, and it's going to allow for the justification of the idealizations problematized by Chua. So we're going to see that in these cases it seems that we can avoid the problem of idealization Chua proposes. It's also going to allow us to diagnose what I take to be true, which is the idealizations that I problematize about Hawking radiation aren't as easily justified. They get some justification, but the difference between these two cases is again well diagnosed by the large-scale structure of what I call deidealization. Okay, so my theses are going to be Chua's problematic idealizations can be satisfactorily justified. The idealizations I problematize are less well justified, and the justification of both of these and their differences are best analyzed with the large-scale structure of deidealization. I'm going to present Chua's idealization paradox/problem for black hole evaporation arguments. I'll then take a step back to some philosophy of science, introduce the large-scale structure of deidealization. I'll use this to justify Chua's problematic idealizations, and I'll repeat this, hopefully if I get time, I might be a bit rushed at the end, but I'll repeat this for my problematized paradoxes and discuss the differences. A Norton presentation style, I talk about quite bespoke physics, which most people, quantum field theory and curved space-time isn't everyone's cup of tea. So I tried to triple track my talks, but people still seem to come away being, not having enjoyed them too much. So I've got a new style. Gold boxes are going to appear on occasional slides. These are the top lines. If you just look out for gold boxes, these will orientate you in the talk and understand the sort of main moves through the argument, which will help you follow it. Black boxes are going to be the key takeaways from individual slides, and then everything else from technical details to minor comments which aren't particularly interesting is white text on a black background. So hopefully this will be able to keep everyone upgoing if you don't actually care about killing vector fields and all of that good stuff. Okay, so let's get into it. So the model which Hawking uses to derive Hawking radiation, and basically everyone uses, is a model of a black hole formed by the collapse of stellar matter. And then once the black hole is formed, it's unchanging for all time. So in physics terms, we call it stationary. But all you need to know, it's unchanging. It's a time translation symmetry. I'm going to refer to this guy as collapsed Schwarzschild throughout, and it's represented by this Penrose diagram with this region being the collapsing matter. But if you don't know what's going on in this diagram, don't worry. All you need to know is that once the black hole is formed, we treat it as unchanging. We derive Hawking radiation, and then we infer to the fact that black holes evaporate. So we replace that diagram with a diagram of an evaporating black hole. The radiation causes the black hole to lose mass and shrink, and eventually disappear. That's represented by this guy, which I'm going to call evaporation Schwarzschild. But again, you don't need to know the details of how this is doing that representational work, except that this guy is changing over time and the black hole is shrinking. So what we want to know is we want to, at least in the case of black hole evaporation arguments, we're going to assume that Hawking radiation exists for now. And we're going to try to get to the conclusion about what effect that radiation has on the black hole. So we're going to assume that there's a net flux going out to infinity. What we're really doing is we're trying to solve this equation, which is the semi-classical Einstein equation. We assume that Hawking radiation flows out to infinity, and we want to figure out what effect that has on the stress energy tensor and how that back reacts on the metric, so we know how the gravitational contribution evolves. There's multiple ways you can calculate the behavior of the stress energy tensor. We can explicitly compute it, and this was done back in the 70s and early 80s, and that gives the result that black holes evaporate. But that's not the set of arguments that Eugene focuses on. Eugene focuses on a completely different set which invoke energy conservation. So we're going to only focus on those. We're going to derive the effect of emitting radiation on the black hole using energy conservation. Now, in general relativity, for reasons which I'm not going to getting into for reasons of time, we only have energy conservation guaranteed in two circumstances. One, if the space-time is unchanging, which we call stationarity, and the other, if the space-time is, in some sense, isolated, which really means as you get increasingly far from the stuff that you're interested in, the space-time becomes flat. And we call this asymptotic flatness. So if we're going to argue for black hole evaporation by energy conservation, we either require an unchanging or an asymptotically flat space-time. So let's focus on the first, as Chua does. Let's assume that let's use the unchanging nature of our space-time. Now we do have this, because in this model we use to derive Hawking radiation, in the exterior of the collapsing matter, the space-time is stationary. There's a time translation symmetry. Remember I said that the black hole doesn't change once it's formed. So because it's stationary, we have global energy conservation. So if you put a big sphere around the black hole, and we assume this flux is going out through this sphere, by global energy conservation, there must be less energy left inside the black hole. So we can infer to there being a negative energy flux down towards the black hole. We've got a negative energy flux over the event horizon. This is going to cause the black hole to lose mass and energy and therefore evaporate. Great. But notice what we've done here is we've assumed this original collapsed Schwarzschild model of the black hole and then inferred to the fact that we're in an evaporating black hole. So we've changed the model of the black hole we're using. But by switching to a changing, evaporating black hole, we undermine the grounds for our black hole evaporation argument. And we can leverage this into a paradox. We can assert four premises which are going to be mutually inconsistent. One, so this is my formalization of the paradox. Chua doesn't quite put it this way, but I find this most helpful. If the space-time is stationary, then energy is conserved globally. If energy is conserved globally in black hole evaporation spacetimes, then black holes evaporate. If black holes evaporate, then black hole spacetimes are not stationary, and then the black hole spacetime is stationary. These four are clearly mutually inconsistent. From 4 and 1 we can derive 3, and then we've got the negation of 4. This is seeming to be a problem, but we've just learned that black holes aren't stationary, they evaporate. So shall we just reject 4? But if we reject 4, we can't then use 4 in conjunction with 1 to derive, and 2 to derive black hole evaporation. And so we're either in an inconsistent place, or in a place where we can't derive black hole evaporation, at least using this energy conservation argument. But remember that our only option wasn't stationarity. The title of the slide is one which should be asymptotic flatness. Stationarity is merely a sufficient condition for global energy conservation in general relativity. We can also use asymptotic flatness. In general relativity, in an asymptotically flat, remember that meant basically isolated space-time, we can use a 3+1 decomposition, and in the Hamiltonian formulation, it's the boundary term, which is the non-zero energy term, which describes the energy of any given space-like slice in the spacetime. And importantly, evaporation spacetimes can be asymptotically flat. Indeed, evaporation Schwarzschild is asymptotically flat. And so there's no paradox here. We're not necessarily undermining our argument by having black hole evaporation. Chua is aware of all of this physics, and so he has what is now not a paradox, but an idealization problem. We would say our universe is not asymptotically flat because it's expanding. An expanding universe is one which is asymptotically de Sitter. If you don't know what that means, don't worry. It basically means that as you go out to infinity, you don't get to a space-time which looks like Minkowski. It doesn't look like flat space-time. Because our universe isn't flat, we don't have the guarantee of global energy conservation. So we say black hole evaporation arguments require global energy conservation. In the context of black hole evaporation, we can only be sure of global energy conservation if the spacetimes are asymptotically flat. Astrophysical spacetimes are not asymptotically flat, therefore black hole evaporation arguments fail. So in summary, the black hole evaporation arguments contain an idealization, asymptotic flatness, which undermines the derivations. Note there's a bunch more idealizations going on in these models. We assume that the only thing in the universe is a black hole. We ignore all the dust and stars and galaxies in the intervening period, right? There's a bunch of idealizations going on, but the only one that Chua focuses on in this case is asymptotic flatness. And so notice that this is just really an instance of our general idealization problem at the start. We've noticed there's an idealization in our model, and we've just worried that this could be messing up our inferences. And so the idealization seems to be threatening skepticism about black hole evaporation. Good. So let's take a step back and think a bit about how we might introduce a framework for solving this problem. So to get the large-scale structure of deidealization off the ground, I'm first going to present the large-scale structure of inductive inference. And to do that, I'm going to go even further back in John Norton's extensive catalogue to the material theory of induction. I'll note here that the material theory isn't going to be necessary, but it's good for helping get the large-scale structure of inductive inference off the ground. So John thinks that good inductions are warranted by facts. And his famous example of how facts warrant inductions is to ask, how did Marie Curie infer from less than a gram of radium chloride in a lab in Paris to the crystalline structure of all samples of radium chloride? Well, it's because we had a fact, and that fact was the uniformity of crystalline structure over samples of salts. Why couldn't Marie Curie infer from her tiny sample of radium chloride to the fact that all samples of radium chloride were in France? Well, it's because we don't have any fact which is guaranteeing uniformity of samples of radium chloride over spatio-temporal position or being within a particular political border. And so certain inferences, and this is just what John takes to be a standard inductive inference from a few samples to all samples, it's allowed because we have a fact, and so this would be contrasted with sort of Hempelian Raven cases. If we had a fact about the uniformity of blackness over, of colour over bird species, then this, from a few ravens to all ravens are black would be an allowed inference. So it depends upon what facts we have available to us. So this prompts the question, how do we know these warranting facts? How do we know this fact about the uniformity of crystalline structure over samples of salts? Well, that's going to be further inductions. We've done more science, we've done more confirmatory science in the past, and that allows us to know these facts. And this leads us to the large-scale structure of inductive inference. The key idea is that inductions are warranted by their embeddedness in a much larger architecture of theoretical and experimental knowledge, which is mutually supporting, has complicated connections, builds up from some contact with experiment all the way up to a large cathedral of knowledge. So this is actually I don't know if anyone recognises it, this is the central lobby of the Cathedral of Learning, which John took, and I did ask John permission to use this. Note that believing this, that understanding scientific confirmation requires situating any particular bit of science in a much larger architecture of science, doesn't actually depend upon you believe in the material theory of induction. You can be material, or you can be Bayesian about induction, or you can think it's abduction. But if you're, for example, a Bayesian, what you're going to think here is, rather than updating your credence based upon one bit of evidence A, you always have to update credences based upon a much larger set of scientific knowledge. Something like that. So it's foregrounding the importance of a much larger architecture of knowledge. Similar if you think IBE is the way to go. And so the key takeaway for me is that confirmation is powered by lots of other scientific knowledge. And what I like about the material theory, about the large-scale structure of inductive inference, is when you go and read any good history of science, at least history of physics, which is mostly what I read, this seems to be how physics is done in the wild. Theorists know a bunch of experiments, and know a bunch of theory, and then they get a bit more theory or evidence, and then the situatedness of that new theory or evidence implies more facts because they have a really large scope of knowledge. And so I think this is really descriptively successful. Good. So we've got the large-scale structure of inductive inference. Now let's talk about deidealization and try to combine them. Idealization is so prevalent in physics that it has its own canonical joke. I'm sure you've all heard it, but just to repeat it, there's a milk production problem at a dairy farm, and so the farmer writes to the local university. The physicist returns to the farm saying, I have the solution, but it only works in the case of spherical cows in a vacuum. Ha ha ha. Now, it's a good joke, but there's a problem with it. I don't mean to like kill the joke by butchering, by analysing it too much. But it's his claim that it only works, which isn't the claim of physicists. A physicist would go back and say, I've only modelled this for a spherical cow in a vacuum, but don't worry, this is going to be perfectly good for real cows in the field. I'm really good at my job. And so we have a question. Physics generically overcomes our general idealization worry. How does it do this? How can we use spherical cows to accurately represent real cows in the wild? What we're asking here is questions of the justification of idealization. As a clarificatory note, there's two notions of justification you might use. One is, why do we, as physicists doing science, choose to idealize? And that could have answers like we are finite beings, we have particular focuses, whatever, whatever. That notion of why do we do the practice of idealization is not the sense of justification I'm interested in. I'm interested in the sense of justification of why doesn't idealization disrupt our scientific goals, in particular in this case, our predictive goals. We want to know certain things are true about the world given our models. Why don't idealizations mess that up? So there's a bunch of approaches to the justification of idealization in the literature, and I'm going to group them up in what I'm going to call traditional deidealization. And they look a lot like that transforming models approach that I talked about at the start. So McMullen talks about adding more parameters back into deidealize. Norton in other work talks about transforming idealized models into approximate models. Natilla and Morgan talk about reversing idealization somehow, etc. So these are all, you've got a model and you have to do something to that model to make it a different model which is going to be more justified somehow. But this traditional deidealization faces both the regress problems and the descriptive problems I talked about earlier. And so I'm proposing the large-scale structure of deidealization as an alternative to this traditional view, which is hopefully going to be more successful at justifying idealization, especially at the edge of empiricism. A further bit of clarification when we talk about justification of idealizations. There's two types of question we might ask, and it's cut off at the top, but I don't like these names, so if anyone has better suggestions for names, they are strongly encouraged. But a type A question, it asks, are we justified in believing the conclusions of models or arguments which are idealized? And type B asks, why do the arguments get the correct answer despite being based upon false premises? So type A questions are in a sense about the world. We want to know if certain claims about the world, the conclusions of our argument, are true or false. And it might be called the scientist's worry, in the sense that once the scientist knows that they're making true claims about the world, they've to some extent discharged their vocational duty. They've gone, yep, I've done good science, I've made predictions which I can be confident or well described in the world, and they can move on. I know that this is a confirmation problem now. We want to confirm the conclusions of particular arguments or derivations from models. Given it's a confirmation problem, what we're going to do is we're going to import our favourite theory of induction, whatever that might be, and the large-scale structure of inductive inference, which, as I've tried to suggest without a full defence, is very important for doing any reasonable scientific confirmation. And we're going to try and solve this confirmation problem. Type B are more about the model. These are asking, why does the model get the right answer, despite it having these false premises or omissions, idealizations in it? And this might be thought of as the philosopher's worry, because even if we know a model is getting the right answer, it would seem to be dereliction of the philosopher's duty if they then go, oh, well, this is fine, our model's getting the right answer, we don't need to look any closer. I don't mean to sort of reify a strong distinction between scientists and philosophers. I think it's just a helpful heuristic for understanding this distinction between types of question we might ask. Now note that these aren't independent. So answers to type B questions are generically going to provide answers to type A questions. If we understand why models get the right answer, then we're going to have good confidence that they do get the right answer, typically. But answers to type A questions don't necessarily need to be answers to type B questions. We can understand that the models are getting the right answer without necessarily understanding why. And I'm going to try and show some cases of this as we go. And so note that answering both of these questions are issues of confirmation. We want to know that certain things are true, certain things are satisfactory explanation. We want to have certain knowledge available to us, which makes us feel like we understand that and why models are getting the right answer. So the large-scale structure of deidealization can really be summarized as a claim that the justification of idealizations, both type A and B, comes not from our ability to deidealize by necessarily transforming the model, but by models' embeddedness in a much larger architecture of scientific knowledge. So it's foregrounding the situatedness of a given model in much larger sets of empirical and theoretical knowledge to make us feel confident that we have good answers to both type A and type B questions. So let's take a really trivial example. Take beta decay, the beta decay of a neutron into a proton. Now at low energies, we know, for a much more elaborate story, but we know that this is well idealized by a Fermi-4 theory, where the neutron decays directly into a proton, an electron, and an anti-neutrino. Now really we know what's going on here is the neutron is decaying via a doubly boson into these things. But the Fermi-4 theory doesn't capture that. For that we need full quantum field theory in all of its standard modelly glory. But we know that this is a justified idealization for any sample of radioactive material we have on Earth. Now consider we have some radioactive material beta decaying on some rocky planet in the Andromeda galaxy. We don't necessarily need to know that this planet exists or where it is. Don't need to photograph it or anything. We just know that there's a rocky planet in the Andromeda galaxy where there's some material beta decaying. We know, despite this thing being completely outside of our empirical purview, that we're going to be able to model it at low energies, assuming it's not particularly high velocities or anything, as with the Fermi-4 theory. And we know that because we know that beta decay and Fermi-4 theory are insensitive to space-time position or galaxy occupation or whatever. And so this idealization is likewise justified. We're leveraging other facts we know about Fermi-4 theory and beta decay to justify treating a certain radioactive material with an idealized model, the Fermi-4 theory, even though we don't have any empirical access to it. I haven't transformed the model, I've just used a bunch more knowledge. I think this sort of thing is going to be fairly typical of how we justify idealizations. So now that I've put forward that, let's see how we can apply it to Chua's problematic idealizations. So first we want type A type justification to the black hole evaporation arguments which Chua discusses. I'm going to propose a general schema for a way that type A justification can be given. I'm not going to say that type A justification always takes this form, but this is a way it can take. In fact, this is basically what happens in that Fermi-4 theory case I just spoke about. There's going to be a situation where we have a successful modelling practice, where a putatively problematic idealization is used elsewhere in physical theorizing and it causes no problems for our scientific endeavour. We then need to know that there are no relevant differences between the success case in one and the case under scrutiny. And then we're going to be able to conclude that the putatively problematic idealizations should not cause any problems in the case under scrutiny. So basically what's happening here is knowing an idealization is safe in other contexts and that there are no relevant difference allows us to import the justification into the case under scrutiny. And so I'm going to say that this schema can be applied successfully to the idealizations that Chua problematizes. So first we need a successful modelling practice. So let's think about how we would model gravitational wave emission from a binary system strongly emitting gravitational waves. First, we would in fact model this system as orbiting in an asymptotically flat spacetime. So two neutron stars or black holes or neutron star black hole pair orbiting, and then far away it becomes Minkowski. We would then calculate the flux carried away from this system. We would then assume that the ADM mass energy is conserved and therefore calculate the energy lost by the binary system. So we're just assuming energy conservation because we've got this asymptotic flatness assumption. We will then deduce that the system has lost energy and the bodies are falling close to each other, and then we'll calculate the decay. And so the asymptotic flatness idealization is also being used in gravitational wave physics. So we've got an instance of a modelling practice, but importantly this modelling practice is successful. Since the 1970s we've been tracking the Hulse-Taylor binary, this is a neutron star orbiting a pulsar, and we'll model this thing with just the sort of framework I just described, and our predictions of the decay rate basically nail the actual measured decay rate of this binary system. So we know that ignoring the fact that our universe is expanding, is in fact asymptotically de Sitter, isn't messing up the modelling of this binary collision. Similarly, we've now got a bunch of gravitational wave detections with LIGO and the new, I forget what it's called, the experiment which measures the gravitational wave backgrounds radiation in the universe. But anyway, this is also going to be using standard energy conserving models to model those black hole binary mergers, and it has a bunch of detections and the modeling practices are going to be working beautifully. And so the idealization of assuming energy conservation for these systems is justified for modeling binary orbits of black holes and neutron stars. We have a successful modeling practice. Now we need to know that there were no relevant differences. That there were no differences under these success cases and the case under scrutiny. And the fact is that the physics, i.e. the conservation of ADM mass in a region where we expect general relativity to be approximately valid, is identical. We can do a 3+1 Hamiltonian decomposition of these systems and detect, and therefore ignore the asymptotically de Sitter structure. In Hawking radiation, we don't necessarily have gravitational waves. Some feature of it will be some proportion of the radiation will be gravitons, but a minority. But functionally, what side of the debate between gravitational waves are energetic or not you come down on, everyone agrees that functionally gravitational waves behave in the exact same way as normal energy, so there's no relevant difference given by this interpretational debate. So basically, whatever we have at the center of our two-sphere, if we've got the approximate validity of general relativity and an ADM mass in a universe with a very small cosmological constant, so it's expanding very slowly, we're going to have the same approximate conservation of ADM energy. There's no differences in the physics. Now, if you're unsettled by the fact that these examples use gravitational waves, think about an even more trivial example. I've just got a hot glowing ball of iron. It could be a star, it could be a ball of iron sat in my lab. And think we can model that system as energy conserving. However, the star or the hot glowing lump of iron in my lab is in fact in an asymptotically de Sitter universe. So how can I possibly model it as energy conserving? Well, the fact is that I can, and it works absolutely fine. And so I can put a sphere around my system, and I can calculate the flux going out through it, and I can calculate the amount of energy left inside. I can calculate the rate with which it will cool. I can use energy conservation in a bunch of contexts, despite our universe being expanding, And so the upshot is that we are justified using our schema in believing that the asymptotically de Sitter structure of the universe, the fact that our universe is expanding, isn't going to mess up our black hole evaporation arguments. The justification of the idealization is inherited from the success of the idealization in relevantly similar contexts. We can also get good type B justification. I do want to put a note that type B justification, we're always going to want it, especially as philosophers in this room, we're always interested in it. But once you've got type A justification, you don't need to keep thinking. So this is a sort of a vindication of physicists who sort of use asymptotic flatness idealizations and don't make any further comment about why this is permissible. They've got type A justification. We know it's permissible. Anyway. So remember that global energy conservation wasn't the causal agent in black hole evaporation arguments. We used energy conservation to infer to some fact about the stress energy tensor and fluxes near the event horizon going across into the black hole. And so what we want to know is what are the effects on these local fluxes, the local energetic contributions of the fact that our universe is expanding to local fluxes. And we know in fact that these are negligible. So for example, we know that a photon propagating through the universe, because our universe is expanding, is going to be redshifted to lower energies. But we know that the amount of redshift that experiences, because the cosmological constant is so small, is going to be tiny. And so you have a huge separation of scales. If the photon propagates over cosmological distances, then that separation of scales breaks down, and you need to model the asymptotically de Sitter structure. For example, gravitational waves propagating from a binary merger to Earth, it involves cosmological scales. And so we then need to involve the de Sitter structure. But at least for the scales relevant to black holes and astrophysical systems that we're interested in, there's a distinct separation of scale. When this separation of scale breaks down, then we can't trust these arguments. So these papers, which I cite by Hawking and Brousseau and Niemeyer and Brousseau, in fact go, okay, what if the scales of the expansion of the universe, if the expansion of the universe is sufficiently fast to be of the same scale as the gravitational effects of the black hole? And then you have to start again, and you have to do bespoke computations to figure out how these effects balance off each other. And in fact, you do still get black hole evaporation, but you can't use our naive energy conservation arguments. And so note that I take we do have good justification for the fact that if Hawking radiation exists, the black holes will evaporate. But we've got this justification from not transforming the models, but just by pointing to a bunch more knowledge we have from our physical systems. So in answering type A questions, I've appealed to other instances of a modelling practice in physics and of empirical success. And then I've also appealed to empirical and theoretical facts about when conservation of ADM mass is going to be expected, to underwrite the induction from the fact that an idealization works for gravitational waves, to the fact that it's going to work for black hole evaporation. In answering type B questions, I've appealed to theoretical and empirical control over de Sitter spacetime. And so I've got confidence that black holes are going to evaporate just by pointing to other bits of scientific knowledge. Good. So I'm actually going to be able to talk a bit about my work, which is nice. My older work. So now let's think about how this all might work for Hawking radiation. So Hawking's derivation of Hawking radiation uses this exact same collapsed Schwarzschild model of black hole evaporation. How this works in detail you don't need to know, except for the fact that we're defining a vacuum state with respect to a time parameter on past null infinity, and we're probing it with respect to a different time parameter at future null infinity, and we're comparing the state probed by these different definitions of positive frequency with respect to different time parameters. And these are related by an exponential transformation, and so this exponential transformation eventually gives you Hawking radiation, because we're defining the vacuum with respect to the past u. And so given the fact that we're deriving Hawking radiation, and once you include black hole evaporation arguments, you can run a very similar paradox to the sort that we ran for Chua. We're starting with our collapsed Schwarzschild spacetime. We're concluding that it's Hawking radiating, and so it's really going to evaporate, and we're replacing it with this evaporation Schwarzschild spacetime, which lacks the structure used to derive Hawking radiation. So we can say, if the spacetime exhibits a set of properties X, then Hawking radiation occurs. If Hawking radiation occurs, then black hole evaporation arguments, black hole evaporation occurs. If black hole evaporation occurs, then the spacetime does not exhibit the set of properties X, and then spacetime exhibits a set of properties X. Again, this is either inconsistent or we're removing our grounds for derivation of Hawking radiation. So, do we have a successful modelling practice which is going to allow us to justify the idealizations used for this derivation of Hawking radiation? And I take it that we don't, because unlike just energy fluxes leaving some region in which we're modelling as energy conserving, what we're trying to derive here is particle creation by a time-dependent gravitational field, which is an entirely novel physical effect. And so there's no successful instance of modelling this physics with the relevant idealizations in another context. The important difference is, rather than just calculating the effects of the amount of energy left inside a two-sphere, which is very standard, we're trying to derive the existence of the radiation due to a new physical phenomenon. Now you might think that we justified these idealizations for the Chua case, why aren't they justified here? Well, if you take them to the modelling practice to be justified for gravitational waves, then the difference would then manifest itself in there being relevant differences. And so there are relevant differences between just calculating the amount of energy left inside a two-sphere around some stuff and trying to calculate itself the original flux. And so the novelty of particle creation due to a time-dependent gravitational field either manifests as there not being a successful instance of the modelling practice, or there being relevant differences. But the schema breaks down. And so we don't get type A justification of Hawking's derivation of Hawking radiation in this way. Now there's different routes to type A justification. We might try to just confirm for ourselves that we're confident that Hawking radiation exists. We're just trying to confirm the conclusion of the model. Various different arguments exist for this. Many different derivations seem to all suggest that Hawking radiation exists. That might give us confidence that the conclusion of the derivation is accurate. There's a consilience argument with black hole thermodynamics. That we might have something like framework conservation, in which the framework in which we derive Hawking radiation is confirmed by perhaps its empirical accuracy in early universe cosmology, and then we might inherit that framework confirmation for Hawking radiation. It might be a uniquely specified theory under some set of reasonable conditions, and then there's analog gravity, in which, for example, hydrodynamic systems seem to confirm Hawking radiation. So these are all reasons. I'm not going to commit to any given one of them. There's a whole talk could be given on each of these, whether they're in fact confirmatory or not. But I'll just note that the way these are trying to justify the idealization is they're justifying that we should believe the conclusion of the model. We should believe that black holes emit Hawking radiation. And then we're trying to inherit the justification of the deidealization, given that we already know the conclusion of the model is right. This seems to be reasonable type A justification, but we need to be careful because the derivation might have got the correct answer for the wrong reason. It might have got lucky somehow. And so this is seemingly type A justification, but it's less satisfactory type A justification than in the Chua case. Now, let's see if we can get some type B justification. There's a challenge for deidealizing Hawking's derivation of Hawking radiation, in that what we really want to do is find a region of our evaporation spacetime which looks about stationary, over which the black hole doesn't evaporate for very much. So the extent to which the spacetime is changing is negligible. However, because Hawking's derivation starts at future null infinity and goes all the way to past null infinity, the quasi-stationary regions of this spacetime are in sort of tick regions like this. And so Hawking's derivation takes us far outside of the region in which you might expect stationarity to be well approximated by the spacetime. In other words, it's taking us out of the domain in which you might have scale separation. This is more talking about why this is a problem. And so it seems that Hawking's derivation doesn't naively give itself to a scale separation argument. Could we deidealize a different derivation? There's many options you could choose. My preferred one is Friedenhagen and Haag's 1990 derivation. I'm not going to get into it here, but it seems like this could get some form of justification of its deidealizations. But note that we wouldn't want to just deidealize this by transforming the model again. At some point you want to get to a model where you stop transforming the model, but the idealizations are just justified by the large-scale structure of deidealization. This seems plausible because the core physics underwriting Friedenhagen and Haag's derivation is they show that any state which obeys what's a usual condition on the physical reasonableness of a quantum field state on a black hole spacetime, the Hadamard condition is going to imply Hawking radiation. So any state which is Hadamard on a black hole spacetime, you're going to get Hawking radiation. This then explains to us why Hawking's derivation gets the right answer, despite perhaps having a struggle being deidealized. Hawking's vacuum state was Hadamard, so it satisfies this sufficient condition. Now, this is a universality argument, so it's a claim about all physically reasonable states, which is why it subsumes Hawking's derivation in quite a satisfactory way. What then justifies the Hadamard assumption? What we don't want to do is keep transforming the models. But it seems that the Hadamard condition is going to be justified by a bunch more further inferences and inductions, and a bunch more knowledge about what quantum field states are going to be physically reasonable on black hole spacetimes, i.e. from its embeddedness in a much larger architecture of empirical and theoretical knowledge. And so I take it that the large-scale structure of deidealization has been exhibited again. To answer type A questions, I appeal to other bits of theory, for example, other derivations, analog gravity. This was to some extent unsatisfactory, though, due to the lack of empirical embedding of all of this in science, or at least less satisfactory than the Chua case. Type B, I appealed to other derivations, and these other derivations were seemingly better embedded in empirical science and relied on other knowledge that we had, for example, the justification of the Hadamard condition. And so I take it that, again, we're understanding all of the success and failures of the various idealizations, the deidealizations, due to their embeddedness in a much larger architecture of scientific knowledge. And so bringing it all back home, I take it that I hope to have presented the best case for deidealizing Chua's and my black hole idealization paradoxes. I take it that these deidealizations both have some degree of success, but differing degrees of success, and that these deidealizations and their respective degrees of success are best understood via the large-scale structure of deidealization. Now, I wanted to talk a bit about how this fitted into a larger thinking about epistemology at the edge of empiricism, but I don't have time, so I'll shut up there. Thank you very much.